Hello, everyone. I would like to talk about the relationship of law and the checking of consistencies in legal contracts. And so the talk by Rüdiger and Scott is an excellent introduction into this field. And by chance, we met in the fall, right, at NYU, and we didn't know of each other that there were these similar activities. And so we had a chance to talk about the state of things as they were in the fall already before. And so this is joint work with Alan Khoja, Martin Kölbl, and Rüdiger Wilhelmi. Alan Khoja and Rüdiger Wilhelmi are law persons. Actually, Rüdiger Wilhelmi is a colleague on the faculty of our law department. And the interest in logic and law is historically quite old. I'm not sure whether this is the first approach towards it, but I'm aware that Leibniz in the 17th century already stated that in the field of legal conditions it will be shown that certainty and proof exist in law. And in particular, the proof aspect is something that we are pursuing here. Later there was lots of developments in deontic and defeasible logics, and my understanding is that we will hear quite a bit about these kinds of logics during the day as well. Now, what I want to focus on is sort of a question, is law code? And we all know that an insight from sort of like software program verification is that software is logic at work. And so if we're saying that software is identical to code, then the question is logic at work. And the question is posed in particular because we want to see whether we can benefit from methods for software verification. And in the keynote talk, this was already so very well explained that we can do that. We want to focus here on looking at an analysis for inconsistencies and non-executabilities of legal contracts. So an example here that I'm going to use is that Eva is selling a pretzel bakery. Notice that this work was done in southern Germany, so where pretzels are relatively famous, right? And it's selling it to Chris, and it's attached with a warranty of 10,000 pretzels capacity per day. And actually, we're assuming that this is violated, and so the contract says that after 29 days after the signing date, Chris is asserting the warranty, which means that 71 days there is the due date for the warranty claim, and 70 days after signing, the limitation for this contract is taking place, so that in essence this warranty is not covered by the contract. It's these kinds of inconsistencies that we would like to automatically analyze. So what is the approach that we're taking? We're saying that contracts are basically complex collections of claims. We are restricting ourselves to sales purchase agreements here. That is a little bit opportunistic because these agreements typically exclude sort of the background legal system. So the only facts that hold are inside this contract, and at a later point, of course, we want to look at other types of contracts as well, but in the first step, this is what we're pursuing. Contracts, like software during development, change very often during the negotiation phase, and it would be very desirable to have something like a red flag system that would flag inconsistencies in the contract. So what we need is automated analysis, and we're interested in dynamic consistency analysis. Can each claim be performed individually? Does there exist a contract execution at all? And we want to talk about timings and other domain-specific properties. The contract check approach is as follows. So the steps in the contract executions are basically sequences of assertions and performances of claims. And what we're doing is we're setting up these claim executability first-order logic predicates, and we're using something like a weakest precondition semantics in order to do that. So we're saying that if the precondition is satisfied, then the executability of a contract is given. So an example is that we're saying a contract starts at a date DS0, then DC is the performance date for every claim. -1 means the claim is not performed. LC is a Boolean condition saying that the claim is performed. And then we define this claim executability predicate, which basically says that the execution is between the due date and the limitation. And the objective is that we want to encode the claim in decidable fragments of first-order logic, as you had already also suggested, and that we use an SMT solver in order to establish the claim and the contract executability. Now, how did we proceed? One of the first steps we actually did was, together with our law colleagues, was to come up with a contract ontology. So we're looking at sales purchase agreements, and we were coming up with what is a contract at all? So it's a purchase agreement, which was a very important step, and that also the legal colleagues found very helpful. I'm depicting it here using an UML class diagram, so it talks about claims, primary claims, secondary claims, and other aspects. Second step is then that we are translating the sales purchase agreement into the clauses in it into a set of blocks based on this ontology. And the way we're doing it is basically by taking the text, by manually mapping it to sort of some parameterized text block, which is kind of like structured parameterized English, and we feed that into our ContractCheck tool for further automatic processing. So the workflow inside ContractCheck is the following. We're translating these blocks into an internal representation. We're using UML object diagrams here, but this is not something the user needs to edit. This is done automatically. So they represent an instance of a contract according to and consistent with this ontology. We formalize that in SMT2 lib code. We stick it into the Z3 SMT solver and depict results. And I'll show you a few examples of how that is done. So the formalization is, we already had seen the formalization for basic claims like pay claims or transfer claims. We can equally handle warranty claims, which are independent secondary claims according to our terminology. And so we're encoding that the warranty is met. The claim does not to be invoked. Otherwise, it is breached. The warranty is breached on a certain day. And again, we're coming up with such a formula that indicates whether the precondition for this warranty claim is actually satisfied. There are further consequence claims, and I don't think I have really the time to go into all of the technical details here, and please have a look at our papers in order to get more information. But we're having performance claims that we can formalize. We're having restitution claims when somebody withdraws from a purchase agreement, and we also have compensation claims for the violation of certain warranties, for instance. Now, we're putting this together in defining what a contract is. Basically, what we are inferring from the facts that we have inside the contract is property rights. So the property rights have to be satisfied, and then we have the primary claims and the independent and secondary claims, and again, their performance is then basically checked, and the satisfiability of this fee SPA formula is checked by an SMT solver. What we can also do is, and we had some discussions on that, Scott, when I present for the first time, is that we can put some preference on primary and independent claims. Independent of the argument that you mentioned, efficient breach would probably not be, or means that this is not necessarily something we should recommend our customers, but this is something where we can do a sanity check and check whether an execution of the contract using primary claims is possible at all. And the good thing, or the interesting thing, is that we are in an SMT solver, we can define these partially satisfiable max SMT problems that allow us to express certain preferences for violating certain rules in the sense of making the whole system a satisfiable constraint system. And so the contract execution is then described by this partially satisfiable max SMT problem. Okay, so analysis, we're defining two types of analysis. The one analysis is that we're asking ourselves, can each claim be performed individually? for which we have basically this claim formula and the ensuing secondary claim formula if they are violated. And when asserting all claims and consequence claims leads to a satisfiable constraint system, then every claim can be performed. The second analysis is, does there exist at all an execution of the whole contract? Because it could be that some claims are not satisfiability, but still the contract can be performed. So in the example of our pretzel bakery, we have a transfer claim, and we're doing a little bit of a trick here right now. We don't yet have a distinction between information that's inside the contract and what's in the environment, so we are encoding the fact that the bakery has actually been transferred to the bank as a security for a loan or a mortgage into the contract. One would not usually probably not do that. But using functional consistency reasoning with uninterpreted functions, the SMT solver is going to show us this inconsistency, and so it would red flag and say these two blocks in the contract are in contradiction, obviously. We have pay claim analysis, pretzel warranty analysis. We're getting satisfying models, and the great thing is that the SMT solver is actually providing satisfying models, and thereby it's showing us possible executions of these claims. We have a compensation claim analysis here. This is the example that I initially showed you, where we are basically putting in, and we're actually reasoning about the numbers here, the integers that tell us distances compared to the signing date of the contract. And we're getting an unsatisfiability core that tells us, okay, there's a de-warranty. If we're asserting the warranty at time 29 after signing, then we're getting into this contradictory or inconsistent execution. A last example that I want to briefly show is that we're kind of like analyzing this pretzel bakery contract, and we're getting an execution where no transfer of shares of the bakery is happening. The price is actually being paid on day 28. There's no warranty, no pretzel consequence claims. There's no compensation that's happening. There's also no restitution. But there's a restitution of the seller, but there's a restitution of the purchaser, which has paid the price, and that leads to this execution of the contract. And what this example shows is that even a contract that is in some sense contains important inconsistent claims can be executed, and this is a scenario that the system would then return for us. What are if we look at an assessment, strength of the contract check is that this SMT-based reasoning allows us to reason about different decidable quantifier free theories. So we used integers, uninterpreted functions, equalities, linear arithmetic. It provides models both in satisfiability and unsatisfiability cases, full automation. The max SMT solving allows us to implement certain theories. We find that finite executions are most useful. There are some approaches in the literature that use LTL-based formalizations, but we have not really come up with a case where we would want to look at infinite executions and would like to specify liveness properties, for instance. This block approach seems to nicely align with existing tools in the law industry, contract generation tools, and we hope at some point to be able to incorporate that into some existing tool as well. What is future research we're planning to do? We're planning to work on a more concurrent, perhaps state machine-based model for the dynamics of the contract execution. We want to incorporate or to devise this or better respect this contract environment distinction. We want to look at more complex contracts, something in the works right now. And then we want to certainly go into something like advantageousness assessment. So we want to feed back to the user for which party in the contract a certain situation is advantageous, what kind of risks could be associated, for instance, in the first case. And so we need to explore links, for instance, to game theory here. This is really not something we've done yet, but it is something to be considered in the future. And what we're currently working on is actually on the front end. We want to work on using machine learning-based text analysis in order to directly map contract text to these blocks in order to facilitate and to avoid the manual encoding of these blocks. We have about 1,400 pages of contract text templates, largely taken from textbooks, both in German and in English, more in German, but also quite a bit in English. And so we're starting to work on labeling these, getting students to label them, and then learn an existing language model in order to do that. Now, what have we learned as a conclusion? I think to some extent, law is logic is code. Not all of it, but there is really quite some analogy. Software analysis techniques, or techniques that I think have been driven arguably most importantly by software analysis needs, are applicable to legal systems. Mechanized logic can be very effective, in particular this SMT solving, because it provides really constructive answers. And of course, automation, like in software engineering, is key. There's a couple of papers where more information can be found. The first one is sort of the extended abstract for this talk, and the Spin 22 paper where we describe this more in detail. And with that, I want to thank you for your attention, and I'm happy to answer further questions.
Thank you. We have plenty of time for questions, so let's start with questions from the room.
Yeah, should work now. I wanted to ask you, what's your methodology for validating that the formal model that you did of the contract was actually correct with respect to the text of the contract and the interpretation that could be made of the text of the contract? Did you have a lawyer in the room who could read the code, or did you have another methodology?
Well, okay, so what's important to notice here is really that half of the team is lawyers, right? Alan Khoja is a PhD student in the law department, and Rüdiger Wilhelmi is a professor, right? So really it was forward engineering. We sat together, and so in particular Martin and Rüdiger, they sat together to form this ontology, right? And they met numerous times, and actually what Rüdiger appreciated was that really this sitting down and thinking about how can you depict such an ontology, what's important in it, clarified for him so many things that he had never really thought about before, right? And this I think coincides with experience in software design, where just thinking about a specification clarifies so many issues that you have, and it's very similar here. So we don't have an ex post verification step. It's kind of like forward engineered.
Thank you. We have a question in the chat. How do you deal with exceptions, and how are obligations, permissions, prohibitions handled?
Okay, so exceptions, I think, are sort of like these secondary claims, like when warranties are breached. I think there's a possible other interpretation, like if the contract is executing, right, and something unforeseen happens, right. We're not currently dealing with that, right. That will be part of if we move forward towards a more, let's say, a more sophisticated execution model. The aspects of obligations and so on are really aspects in the realm of deontic logics, deontic approaches. This is not really something that we can handle in this framework, right? So we're looking at basically executability of the contract.
Any more questions?
Thank you. Because getting the formalization right is so important, how do you know that the machine learning techniques you're using are getting it right without doing manual inspection, or do you do it in addition?
Okay, so the machine learning is supposed to do sort of like clause in natural language text to block translation. That's at least the approach we're currently taking, right? And we haven't done it yet. It's on the agenda, right? So we'll have to find a way of assessing the accuracy of this machine learning, of this text translation technique then, right? So is a clause correctly translated into a block, right? Or mapped, classified as being a certain type of block. That will probably be a manual step, but I don't yet know. I think probably the system is going to be sort of like a 98% system in which it works well, and then there's going to be a number of cases where the system is going to say, I have no idea what kind of clause that is, where you need some manual inspection. But assessing the accuracy of that is certainly important.
But I guess the worry is not that the algorithm doesn't know how to encode the clause to the block. It's that it's the 2% that it does the wrong block. I guess the question is like methodologically. So the great thing about automated reasoning is that you get the right answer. But the thing about machine learning is you don't necessarily. So
right.
So
I agree. We'll have to think about some quality assurance mechanism at that end. Yes, if this classification is wrong, then your result is not going to be. Also, I think a justification is that this is going to be kind of an advisory system, right? It's not to replace the lawyer, right, or the legal expert.
Thank you.
I think there's a question, I think, over there.
One last question, and then we'll move on to the next talk.
In the development of this ontology, were there any particularly tricky points to formalizing this model, or that the experts that you had may have been in conflict or debated?
Okay, I think so it was one legal expert who was not in conflict with himself, right? And it was my PhD student, and I think they for a very long time they talked about like what are claims, how do we need to classify them, right? That was really one of the important and challenging issues, and I'm still not sure whether this is the ultimate answer for that, right? But they really sat together and tried to come up with a coherent answer.